Last time we wound up the clock, you hand it the state, the where and the how fast of everything, and it grinds the whole future out of that one frozen instant. And then, right at the door, you dangled something in front of me and refused to explain it. You said there's a shortcut. A single number that just sits there, refusing to change, while everything else moves. And somehow that one stubborn number tells you where a thing is allowed to go, without your ever turning the crank. I've been chewing on that since. It sounds like a cheat code, and I don't trust it yet.
You shouldn't trust it yet, but you're about to. That's the whole of today. Last episode was labor. The machine works, but you turn the handle step by step by step, and for most of what you want to know, that's a punishing amount of turning. Today we buy our way out of nearly all that labor with a single quantity that holds still while the motion churns. Its name is energy, and it lives in a landscape, hills and valleys you can literally draw, that a moving thing rolls around inside.
See, that's the sentence I can't swallow. One number that holds still. A trajectory is a whole unfolding story, where the thing is at every moment, how fast, which way it's turning. How can one frozen number stand in for all that motion? It's like telling me a single word can stand in for an entire novel.
It doesn't stand in for the motion. That's the thing to get straight before anything else. It doesn't tell you the story. It fences the story in. Think of it less like a summary of the novel and more like a rule the whole novel is forced to obey. The number can't tell you the path the thing takes, but it can tell you, flatly, which paths are off the table, where the thing simply cannot go, no matter what. And that fence gets drawn so tightly that, an awful lot of the time, you can just see the answer without solving anything.
A fence, not a summary. All right, I can hold that, provisionally with one eyebrow up. So there are 2 stars in today's show, this stubborn number, energy, and this landscape it hides in.
Those 2. And they turn out to be one idea, seen from 2 sides, which is the thing I most want you carrying out the door. But I can't just hand you the landscape yet. It wouldn't mean a thing. First, I have to tell you what energy even is, because I'd bet the picture in your head right now is wrong, and wrong in a way that'll fight us the whole way if we don't clear it out first.
Oh, I've definitely got a picture, and now I'm nervous about it. Energy is, I don't know, a kind of glowing stuff? A juice. Like there's fuel loaded into things, and when they move or heat up, the fuel sloshes around or drains out. That's the cartoon in my head. A tank of glowing energy stuff.
That's the cartoon in nearly everyone's head, and we have to set it down. Energy is not a substance. There's no glowing fluid, nothing sloshing, no tank. Energy is a number, a bookkeeping number. You add up a few things according to a recipe, and you get a total. The one strange, powerful fact about that total is this. As the thing moves and shifts and changes, if you keep the books straight, the total never changes. It sits fixed while everything that went into it churns around.
Hang on, never changes is carrying a lot of weight in that sentence. Loads of numbers about a moving thing change every instant. What makes this one sit still?
That's the whole magic word. Conserved. A conserved quantity is one nature holds fixed, no matter what the thing gets up to. You can work it out now, walk away, come back after all kinds of mayhem, work it out again, and land on the identical number. Most quantities aren't like that. They drift and jump around as the motion runs. The rare few that flatly refuse to move are gold, because a number that never changes is a number you can lean on without following every step of the motion. That's why we go hunting for them.
A bookkeeping number that refuses to move, even though everything feeding it is moving. Fine. What goes into the total then? What am I adding up?
For today, 2 things. 2 kinds of energy that trade back and forth. The first is the obvious one. The energy a thing has simply because it's moving. A rolling ball has it, a parked ball doesn't. The faster it goes, the more of it carries. We call that kinetic energy. Kinetic just means of motion, energy of movement.
Okay, energy of motion. A thing that's moving has some, a thing sitting still has none. That one matches my gut.
It does, with one wrinkle I'll come back to that catches people out. The second kind is sneakier, because a thing can have it while sitting stock still. Picture a boulder resting right at the lip of a cliff. It isn't moving, no kinetic energy at all. But everyone looking at it feels that it's loaded, dangerous. One nudge and it's a disaster. Where's that menace coming from if the thing is just sitting there?
From how high up it is, from where it is. If that same boulder were sitting on flat ground, nobody would flinch. It's the height that makes it feel loaded, the fall it's got waiting inside it.
The fall it's got waiting inside it. That's the phrase to keep. That stored, waiting energy, the energy a thing has because of where it is or how a system is arranged, is the second kind. Potential energy. Potential as in latent, held in reserve, not yet cashed in. The lifted boulder has it. A stretched spring has it. You did work bending it, and now it's holding that, straining to snap back. Potential energy is position or arrangement, waiting to turn into motion.
And is it always height, or is a stretched spring a different flavor of the same thing?
Same thing, different arrangement. Height is one way to store it. Lift a weight up against gravity, and you've loaded it. Bending a spring is another. You push its coils out of their happy shape, and they strain to snap back. Drawing a bow, winding a clockwork, pulling two magnets apart. Any arrangement that's straining to change, holding energy it would let go if you released it, is carrying potential. Position is just the plainest version of it.
So kinetic is the motion you can see, and potential is the motion you're owed. Motion in waiting.
That's a clean way to put it. And now the deal that runs this whole episode, the single most important sentence today. Those two are forever trading places, and their sum holds fixed. When one grows, the other shrinks by the very same amount, so the total across the two never budges. Kinetic can pour into potential. Potential can pour back into kinetic. But the books always balance to the same number.
All right, give me the picture where I can watch that happen. Something simple.
The simplest one there is. It's the picture Galileo kept coming back to. Balls rolling down slopes and tossed up in the air. And we'll lean on it all series, so fix it in your mind now. Toss a ball straight up and watch it rise, stop, and fall back into your hand. That's the whole laboratory. Now, you tell me, somewhere in that arc the ball is moving fastest, and somewhere it's moving slowest. Where's each one? Don't compute anything. Use the trade.
Let me reason it out loud. Right as it leaves my hand, at the bottom it's got all its speed. I just threw it, it hasn't lost anything yet. As it climbs, it slows. At the very top it stops. For just an instant, before it turns and comes back. So, fastest at the bottom and slowest at the top, where it stopped. No speed at all at the peak.
Good. Now translate what you just said into the two energies. At the bottom, moving fastest, that's all kinetic, the potential pocket empty. At the top, stopped dead. No kinetic left, so every bit of it has gone into potential, into the energy of height. Going up, kinetic drains into potential. Coming down, potential pours back into kinetic. And the sum of the two is the same at the bottom, the same at the top, and the same at every point between.
So the ball never loses the energy. It just keeps swapping which pocket it's sitting in. Motion energy at the bottom, height energy at the top, and the total is a constant it carries the whole way up and back down.
Carried the whole way, unchanged. That's your first conserved quantity, seen live. And look how it already earns its keep. I never told you how heavy the ball is, how hard you threw it, how high it climbs. You still nailed where it's fast and where it's slow, purely from the two trade, and the sum holds. That's the shortcut starting to pay out.
Before the wrinkle, Is the tossed ball the only place this trade shows up? It feels like it ought to be everywhere.
It's everywhere. Take a swing on a playground. At the bottom of its arc, it's whipping through fastest, all kinetic. At each end of the swing, for one instant, it hangs stopped before it heads back. All potential, all height. The same trade as the tossed ball, just swinging sideways through it instead of straight up and down.
So a swing is really the tossed ball lying on its side. It races through the bottom and freezes for a blink at the two edges.
That's it. And here's the trade showing its hand. A swing left to itself never climbs higher than the height you first let it go from. Not once, no matter how many times it comes back. It can't. There's only so much total to spend, and the height it reaches is capped by it. Push a kid on a swing, and you're topping the total up. Leave it alone, and it settles for just what it started with.
You said there was a wrinkle hiding in the kinetic one. The surprise. I want it now.
Here it is. Kinetic energy doesn't just keep pace with speed, it outruns it. The faster it's already going, the more each extra bit of speed piles on. So a fast thing isn't a touch more loaded than a slow one. It's dramatically more loaded, way out of proportion to how much faster it's going.
Wait, why would the energy grow faster than the speed itself? If I'm going a bit quicker, I'd have guessed I've just got a bit more motion energy, matched 1 for 1.
That's the most common wrong guess about kinetic energy, so it's worth sitting with. And I'll admit the limit here. The exact rule for how steeply it climbs lives in the formula for kinetic energy. The one bit of arithmetic we're deliberately not writing today. So I can show you that it's true without deriving from scratch why it's that steep. And you felt that it's true even without a name for it. It's why a car at a high speed needs so much more room to stop than one ambling along. Far more than the gap in speed would suggest. There's a great deal more motion energy packed in there than intuition budgets for, and every scrap of it has to be bled off before the car can rest. Hang on to grows faster than the speed. It comes back the moment things start moving quickly.
Got it. And potential, the height one, is there a catch buried in that one too?
One point, briefly. When I say the boulder has potential energy because of its height, height above what? The valley floor? The sea? The center of the earth? The answer is your choice, and it doesn't matter. We get to pick where zero height sits, wherever's convenient, and only the drop from one spot to another ever shows up in the physics. Potential energy has no true bottom, no absolute value, only differences, only heights measured from some line you picked. Slide the line up or down, every number shifts, nothing physical changes.
So the raw potential number is sort of meaningless on its own. It's only the change in it, the drop, that's real.
Only the drop is real. Which fits the boulder. What hurts isn't its absolute height, it's how far it falls before it lands. Keep that filed. Only differences matter. It'll keep you out of trouble down the line. Now, we've been watching energy slosh between its two pockets. Time for the question you should be itching to ask. What does the moving? What actually pushes energy out of one pocket and into the other?
Yeah, something has to do the transferring. The ball doesn't just decide, on its own, to trade motion for height. What's the agent here? Gravity, I'd assume, since it's the only thing pulling on the ball.
Gravity, the whole time. And the thing gravity is doing, the process of moving energy from one place or one form to another, has a name in physics. It's a word you already use, which is going to be a problem because the everyday meaning and the physics meaning don't line up. The word is work.
Work, as in effort, straining, pushing, getting tired.
That's the everyday meaning, and it'll lead you astray. In physics, work is sharper than that. Work is what a force does when it pushes something along through a distance. A force acts, the thing travels some distance while the force is pushing on it. And how hard, over how far, is the amount of energy that gets transferred. Push along the motion and you pour energy in. the thing speeds up. Push against the motion and you drain energy out. It slows. Work is the channel the energy flows through.
Force through a distance. You push and the thing travels while you're pushing. Okay, but back in the first episode, the second law was force through time, wasn't it? A force acting over an interval, grinding the motion forward tick by tick. Now you've swapped time for distance. Is that a slip or does it matter?
It's the hinge of the whole episode, not a slip. Last time, in Newton's machine, we watched force act through time. Hold a push on for a stretch of time and it builds up motion, instant by instant. That's one true way to keep the books on a force. But there's a second, equally true way. Watch that same force act through distance instead. And those two ways of bookkeeping answer two different questions and hand you two different conserved quantities. Force through time is one tool. Force through distance, work, is the tool that gives us energy.
So the very same push, and I get to choose whether I total it up over the time it acted or over the distance it covered. And I get a different quantity depending on which I pick.
A different quantity and a different picture of the world out of each. We'll spend a whole later episode on the time side and what it conserves. Today is the distance side, and what the distance side conserves is energy. Same forces, different question. That's the entire reason physics keeps more than one tool in the drawer.
Quick check on the distance part. If I shove a parked car with everything I've got and it doesn't roll an inch, I'm wrecked afterward. But did I do any work on the car?
Not a scrap. Force, but no distance, so no work. No energy went into the car at all. All that straining went into heat inside your own muscles instead. Work needs the thing to travel while you're pushing on it. No motion, no transfer, however hard you heave. That already tells you the everyday sense of the word is the wrong one. You can labor to exhaustion and, in the physics sense, do precisely nothing.
Let me poke at force through distance. What if the force is there and the thing moves, but the push is sideways to the motion, neither along it nor against it, just crosswise? Does that count?
The answer trips everyone. No, a force pushing dead sideways to the motion does no work at all. None. It can bend the path, steer the thing, turn it, but it transfers no energy, and it changes no speed.
That feels wrong. There's obviously a force, the thing's obviously moving. How is nothing getting transferred?
Because work is force along the motion, and a pure sideways push has nothing along the motion. It's all across it. Picture carrying a heavy suitcase across flat ground. You're holding it up hard the whole way, your arms aching, and that sure feels like work in the everyday sense. But you're pushing straight up, while the suitcase travels straight forward. The push and the travel are at right angles. So in the physics sense, you do no work on the suitcase at all. Its motion energy isn't changing. It rolls along at the same speed, whether you strain or not.
My arm would like to file a complaint, but I see it. Up push, forward travel, crosswise, so nothing gets poured into the suitcase's motion. The tiredness is my muscles problem, not the suitcase's energy.
Right, and park that one somewhere safe. Sideways force does no work, because it's the quiet reason a thing swung in a circle keeps a steady speed, and it comes back when we get to orbits, and again when we get to magnetism. A pull that's always sideways to the motion never speeds a thing up. It only turns it.
All right, bring it back to the ball. Gravity, force through distance.
On the way down, gravity points down and the ball moves down. Force along motion. So gravity does positive work on it, pouring energy in, and that's the kinetic energy you watch appear as it speeds up. On the way up, the ball moves up while gravity still points down. Force against motion. So gravity does negative work, draining kinetic back out, and the ball slows. Same force, doing work one way on the fall and the other way on the climb. The trade we watched, potential into kinetic and back again, is just gravity doing work, One sign going up, the other coming down.
So, work is the machinery under the trade. The two pockets don't magically swap on their own. Gravity does work through the distance and carries the energy from one into the other.
That's the machinery under the swap. And now, here's where the whole thing turns into a picture. We've got a potential energy that depends on where the thing is. So let's do the obvious thing that somehow nobody thinks to do. Let's draw it.
Draw the potential energy. Draw it against what? Position?
Against position. Here's the setup, and it works only when the force depends on where the thing is and nothing else. Gravity depending on height, a spring depending on how far it's stretched. Forces that care about position alone, and for those, you can make a single picture that holds the whole force story. I'll flag that restriction once, right here. It's real, and we'll honor it all series.
So the rule is that the force has to depend on where the thing is, and nothing else. Position in, force out. All right, build me the picture.
Build it like this. Along the bottom, left to right, you put position, where the thing is. Going upward, you put its potential energy at each spot. Connect the dots, and you get a curve, a line that rises and dips as you move along.
A curve of stored energy against where I am. So where the curve rides high, the thing's got a lot of potential energy, and where it dips low, it's got little.
Right. Now look at what that curve looks like. It climbs and falls as you go along. High places and low places. Peaks and dips. It looks, for all the world, like the cross-section of a landscape. Hills where the potential is high, valleys where it's low. And here's the move. The thing you're really tracking, the ball, the bead, the mass, behaves as if it were a ball rolling on that very landscape. The picture isn't a chart you have to decode. It's a hillside the thing rolls on.
Hold on, the curve is a graph. Potential energy running up the side, position running along the bottom. It's not a real hill. Why does the thing act like it's rolling on the graph?
Because of the trade. And this is the heart of it. High potential means the curve is high there, a hill. For the thing to sit at a high potential spot, it's had to pour a lot of its energy into potential, which means it's drained its kinetic, which means it's crawling. Low potential, a valley, means little energy tied up in potential, so plenty left in kinetic, so it's flying. So the thing is slow up on the potential hills and fast down in the potential valleys, which is just how a real ball behaves, rolling over real hills and dips. Slow at the top, fast at the bottom. The graph and the hillside give you the same behavior, so you're allowed to simply see the graph as a hillside.
Oh, so the landscape isn't a metaphor I'm meant to squint at and never quite believe. The motion of the thing sliding through its potential is the same motion as a ball rolling on that shape. They coincide.
They coincide. And for a thing moving back and forth along one line, that correspondence holds tight. The speeds and the turning points you'd read off the graph are exactly the ones a ball would have on the hillside. In a moment you'll see the deeper reason. The steepness of the curve is the force itself. So from here on, when the force depends only on position, I won't say, the potential energy is high over here. I'll say, there's a hill here, and mean it. We've turned an invisible piece of energy bookkeeping into a shape you can see and point at. Now let me show you what the shape is good for.
Before I do, does the shape tell me anything past where the thing's high and where it's low, like how hard it's being pushed at each point?
It does, and it's the tilt. Where the landscape slopes steeply, the push downhill is strong. Where it's a gentle grade, the push is gentle. Where the land runs flat, there's no push at all. The steepness of the shape, at any spot, is the strength of the force there. So the picture isn't only telling you where the thing goes fast or slow. Read its slope, and it's handing you the force too. Hang on to that. It pays off in a minute.
That's a bold thing to promise. Go on then. What do I do with the shape?
We've got the landscape, the hills and valleys of the potential. I'm going to add one more thing to the picture, just one, and then you can read off everything. I draw a single flat, level line straight across the whole landscape. That line is the total energy, kinetic, plus potential, the number that never changes. And because it never changes, it sits at the same height everywhere. A level line cutting clean across the hills and the valleys.
One flat line for the total. And it's flat because the total is a constant. It doesn't rise or fall as the thing moves, so on the picture it's dead level.
Dead level, all the way across. Now here's how you read the two pockets straight off the drawing at any spot you like. At any position, the potential is just how high the curve is there. The total is the flat line. So the gap between the flat line and the curve underneath it, the leftover, is the kinetic energy. That vertical gap at any spot is the motion energy the thing has when it's there.
Let me make sure I've got it. The curve is potential. The flat line is total. The distance between them, top line down to the curve, is what's left over for kinetic, for speed.
That's the reading. So watch what it tells you as the thing moves along. Down in a valley, the curve is low, so the gap up to the flat line is big. Big kinetic, moving fast. Climbing a hill, the curve rises toward the line, so the gap shrinks, losing speed. And then the moment the whole thing hinges on. What happens right where the curve climbs all the way up and touches the flat line?
The gap goes to nothing. No gap means no kinetic, no speed. The thing stops.
It stops. And it can't be anywhere the curve pokes up above the line, because there the gap would run negative. The thing would need less than no motion energy, and there's no such thing. So the spot where the curve meets the line is a wall the thing cannot pass. It rolls up to it. Its speed bleeds away to nothing right at that point. And then, because the slope of the hill is still pulling it back down, it turns around and rolls back. Those meeting points have a name. The turning points.
Turning points. Where the total energy line crosses the potential curve, speed drops to zero, and the thing reverses. Because past there it would need negative motion energy, and that doesn't exist.
One thing to nail down before we go on, because it snags people. At the turning point, the speed is zero. So why doesn't the thing just stop there and stay put, the way it rests at the bottom of a valley? Both are spots where it's momentarily not moving. Why is one a resting place and the other isn't?
Oh, because the turning point is on a hillside, not on the flat. Go back to the slope is the force thing. At the turning point, the ground is still tilted, so there's still a push on it, back downhill, even though its speed is zero for that instant. It's got no motion, but it's got a force. At a valley bottom, the ground is flat, so no push, and it can genuinely rest. On the hillside, it can't. It's stopped for a blink and then immediately shoved back the way it came.
That's it. Force even at a standstill, because the ground's still tilted. Now the big one, and I want you to hand it to yourself before I say a word. Picture a landscape with a valley in the middle and a hill on each side, a bowl sitting between two peaks. I drop a thing into that valley with a certain total energy, a flat line part-way up the sides. Tell me how it moves. Not roughly, precisely, straight off the picture.
Okay, it's in the valley, it's got a gap, so it's got kinetic, so it's moving. It rolls down toward the bottom, that's where the gap is biggest, so it's fastest at the bottom. Then it climbs the far side, slowing as the curve rises to meet my flat line. Until they touch, turning point, it stops, and it comes back. Back down through the bottom, fast again, up the near side to where that curve hits the line, the other turning point, stops, comes back. And it just does that. Forever. Rocks back and forth between the two turning points. It's trapped in the valley.
Almost. You've got the rocking dead right, but look harder at the turning point itself. You said it stops. Go one step past that. For that single instant, every last scrap of its energy is up in potential. None left in motion. The gap has pinched shut to nothing. That's what stopping really means on the landscape. With that added, You've read the whole motion clean off a drawing, trapped, rocking between its two turning points, back and forth without end. And you didn't turn a single crank.
And I'll push my luck with a prediction. If I let it go from rest partway up one side, it climbs to the same height on the far side. Every single crossing. Because both turning points have to sit on that one level line.
The same height, crossing after crossing. The two turning points lie on a single level line, so the thing rises to just where it began. No higher, no lower. Then turns and does it again. That's conservation looking straight back at you. It can't overshoot its starting height, because clearing that would cost more total than it's carrying.
Okay, that one actually landed. So the turning points are set by how high I put my flat line, which means if I give the thing more energy, raise the line,
and watch the turning points slide outward, up the hillsides. More total energy means a higher flat line, means the thing climbs higher up each side before it's stopped. It ranges wider across the valley. Keep raising it. Now, what happens the moment the flat line rises above the top of one of those hills?
Then the curve never reaches up to meet the line on that side. The hilltop is sitting below my line now, so there's no turning point over there. The gap never closes. The thing climbs the hill, crests the top still moving, and just keeps going. It's over the wall. It escapes.
It escapes. That's the whole distinction, and it's a real physical divide, not a matter of degree. If your energy line sits below the peaks, you're trapped, bound, rocking in the valley for good. If it clears a peak, you're free. You crest that hill and never come back. Bound versus unbound, trapped versus escaping, and you tell which just by asking whether the flat line clears the hill. And that one question, does the line top the peak, is, believe it or not, the very same question as whether a rocket reaches escape speed and leaves the Earth for good, or slows, stops, and falls back.
That's a big claim to just set down. A rocket leaving Earth forever is the same as my line clearing a hill.
The same. Earth's gravity, drawn as a landscape, is a valley, a deep well, with the planet down at the bottom. A rocket climbing away is a thing climbing the wall of that well, trading motion energy for height, slowing as it goes. If it starts with enough energy, a high enough flat line, it tops the well and coasts away for good. If it doesn't, it slows to a stop at some turning point, some highest altitude, and falls back. Escape speed is nothing but the speed whose energy line just clears the top of Earth's well. The tossed ball rocking in its valley and the rocket escaping to the planets are the same physics at two settings of a single dial.
Let me try a trickier landscape then. Two valleys side by side with a hill between them. And I drop the thing into the left valley with some middling energy. Can it ever get across to the right valley?
You tell me. Where's your flat line sitting relative to that hill in the middle?
If my line's below the middle hill, then the thing rolls up toward it, hits a turning point before the top, and falls back. It can't cross. It's stuck in the left valley, even though there's a perfectly good valley right next door.
Stuck. Walled off from a place it would happily sit, by a hill it hasn't the energy to top. Lift the line a bit, above that middle hill, and now it spills over into the right valley and rattles around both. One drawing, and you can see which rooms of the landscape are open to the thing and which are sealed shut, purely from where the level line falls.
That actually reorganizes a bunch of things I'd filed as separate. The ball I throw and the rocket to another planet are the same drawing, just with the flat line sitting at different heights.
The same drawing. That's what the landscape buys you. A whole sprawl of situations collapsing into one picture you read with your eyes. There's one edge of this worth naming.
Go ahead.
I told you the thing absolutely cannot be where the curve pokes above the flat line, the forbidden region, where it'd need negative motion energy. In the world of this course, that's ironclad. The wall is a wall. Down at the scale of the very smallest pieces of matter, quantum mechanics bends that rule. A tiny thing can, once in a while, turn up on the far side of a wall it never had the energy to climb, as if it slipped straight through. That's a real effect and a whole other course. For everything we do here, the wall holds. The forbidden region stays forbidden.
Noted and sealed. Walls are walls in here, with a small asterisk for the very tiny. Back inside the course.
Back inside. So take stock of what the landscape has already handed you. Fast in the valleys, slow on the hills, stopped and turning where your energy line meets the curve, trapped when it's below the peaks and free when it's above. And not one equation solved, just a curve and a level line, and your eyes. This is a tool we lean on for the whole rest of the series. Now there's one special kind of spot on the landscape I've been stepping around, and it's time to look right at it.
Which spot?
The flat spots. The places where the landscape, just for a stretch, isn't sloping at all. The very bottom of a valley, the very top of a hill. What's special about them? Think back to what the slope of the landscape was doing for us. On a hillside, the thing rolls, downhill. The steeper the slope, the harder it gets pushed along.
Right, the slope is what pushes it. So where the landscape goes flat, no slope.
No slope, no push. Where the landscape is level, there's no force on the thing at all. Set it down there at rest, and it just stays. Nothing rolls it one way or the other. That's an equilibrium, a place a thing can sit still and go on sitting still. And on our curve, the flat spots are the valley bottoms and the hilltops.
So a valley bottom and a hilltop are the same in that one respect. Put the thing there, dead still, and it stays, because the ground's not tilted to push it anywhere.
In that one respect, identical. Both are places of no force. But now do the thing physics always does. Don't just set it down, nudge it. Give it the tiniest push off the spot and watch which way the story runs. That's where the valley and the hilltop split, and they split completely.
Let me try. Valley bottom first. I nudge the thing a hair up the side of the valley. Now it's on a slope, so the slope pushes it. Back down. Back toward where it started. So it rolls back and settles. The nudge gets undone.
The nudge gets undone. The valley bottom pulls it right back home. That's a stable equilibrium. Picture a marble sitting in the bottom of a bowl. Tip it a little up the side, and it rolls straight back to the middle, rocks a bit, settles. Push it, and it fights you to get back. Now the hilltop.
Hilltop. I nudge the thing a hair off the very top. Now it's on the slope just below the peak, and the slope pushes it. Away. Downhill. Further from where it started, not back toward it. So it runs off and never returns.
Runs off, and faster as it goes. That's an unstable equilibrium. The marble balanced right on the crown of a dome. In principle, it can sit there, delicately poised, no force on it at all. But the faintest breath of air and it's gone, rolling off, never to come back on its own. Stable and unstable are both, no force right here. The whole difference is in what a small nudge does. The valley heals the nudge. The hilltop feeds on it.
And does it matter how steep the valley is? A shallow dip versus a tight, steep one. Both stable, I'd guess, but they don't feel the same.
Both stable. Nudge either and it comes home. But the steep one snaps back hard and quick, while the shallow one drifts back lazily. Steeper walls mean a stronger restoring push for the same little nudge, so it hurries home faster and rocks more briskly once it's there. That steepness of the valley is what'll set how fast things jiggle when we get to the springs. But that's a thread for later.
Bowl versus dome. And that's why, in real life, you find things resting in the bottoms of their valleys and basically never balanced on the tops of their hills. The hilltops are resting spots in principle, but the first little disturbance knocks anything straight off, so nothing's left sitting up there.
That's just why the world is full of things settled in their dips and empty of things poised on their peaks. Stable equilibria are where matter comes to rest and stays. which makes them worth a very close look.
A close look at what, though? From where I'm standing, a valley bottom is just the bottom of a valley.
Take any smooth valley on any landscape, any stable dip at all, and zoom way in on the very bottom of it. Closer and closer. And as you close in, whatever complicated shape the valley had from far off, the little patch right at the floor always starts to look like the same simple curve. A gentle, symmetric dip, the same on both sides. Every smooth valley, seen up close at its bottom, looks alike. And that one shared little shape is the shape of a spring, of a thing that, pushed off-center, gets pulled back harder the further you push it.
Hold on, why would that be? You start with all these different-looking valleys, and up close they come out identical. Why does every valley bottom settle into the same shape?
That's the right question, and the full answer is a coming episode all its own. For now, the short of it. It's a spring, which is why almost anything at all, a plucked string, an atom jiggling in a solid, a swaying bridge, the swing of a pendulum, when it's disturbed just a little from its resting dip, jiggles in the same way, ruled by that one shape. Nudge the world gently, almost anywhere, and it tends to rock like a spring. That's why the valley bottom is worth so much. It's where nearly all the gentle jiggling of the world is born.
Okay, I have to stop you, because there's a hole in all of this that's been getting bigger for a while now. This whole tidy picture, the ball rocking in its valley forever, the sum that never changes. It doesn't survive contact with reality, does it? Because real things stop. The ball I throw does not bounce forever. Drag a couch across the floor and it grinds to a halt. Friction stops everything, everywhere. So energy plainly is not conserved. It drains away and things quit. Where's my constant now?
That's the right objection. The one you ought to be a little angry about. And here's the resolution. You're correct that the couch stops. You're wrong that the energy drained away. It didn't leave the world. It moved into a form we simply weren't counting. Watch where.
Moved where? The couch is just sitting there, dead on the floor. Its motion is gone. Where did the motion energy actually go?
Into heat. Drag the couch and the floor under it, and the couch's own feet get warm, a touch warmer than before. That warmth is where the motion went. And here's the thing to understand about heat, the piece that closes the whole circle. Heat is motion. When something's warm, its countless tiny pieces, the atoms it's built from, are jostling and jittering faster. Warm just means the little parts are moving more.
Wait, so warm is really just small-scale motion. The heat in the floor is the floor's own atoms, jostling quicker than before.
Just that. Warmth is motion too small to see. So the couch's motion never stopped. The one big, organized motion of the whole couch sliding got broken up and parceled out to the numberless tiny pieces. And now they're all jiggling a bit harder than they were.
So the motion didn't die, it got scattered, chopped up and spread out into a zillion little motions I can't see.
Scattered is the word, and it's the same word from last episode. Remember, right at the end, when we asked why friction looks like a one-way street, even though the deep laws run backward just fine. This is that. The one big motion of the couch gets scattered into the motion of its tiniest pieces, into a form too fine for us to track, spread across so many little jigglings that we haven't a hope of following each one. We stop being able to see it as motion, so it looks for all the world like the energy vanished. It didn't. Count the warmth, count the extra jiggling, and the books balance back to the same total, right down to the last bit.
So friction destroys energy is just plain wrong. Friction takes the one nice big motion and shreds it into a fog of tiny motions I've stopped tracking. And if I could somehow add up all the tiny ones, nothing's missing.
Nothing is ever missing. Never say friction uses energy up or destroys it. It hasn't got that power. Nothing has. It moves organized motion into scattered motion. tidy into messy, trackable into untrackable. The grand total holds. What friction really costs you isn't energy, it's the organization of the energy. It takes the neat, usable, all pulling together motion of the couch and trades it for a hopeless jumble you can't easily gather back up and put to work.
So when you told me energy is conserved, there was fine print, and this is it. The clean landscape, the ball rocking forever, that's the world with friction switched off.
That's the fine print. The tidy landscape picture, the never-changing sum, is exact for the store and return forces. Gravity, the spring, the ones that hand back every bit of energy you put in. We call those conservative. Friction isn't one of them. It's the leak that carries organized energy off into heat, and the simple landscape sets it to one side. Both things are true at once. Energy is always conserved if you count the heat, and the clean, rolling ball picture is for the store and return forces, where you don't have to.
Can I even see friction on the landscape picture, or does it just wreck the whole drawing?
You can see it, and it's a tidy way to hold both ideas at once. Think back to the swing that dies down, the real one with air and rubbing. Each pass, a little of its organized motion leaks off into heat, so its total sags. On the landscape, that's the flat energy line slowly sinking. And as the line sinks, the two turning points creep inward. The swing doesn't reach as high, then reaches less high, then less, until the line settles right down onto the valley floor and the thing comes to rest at the bottom. That's friction drawn straight into the picture. The clean landscape has a fixed level line, but add friction and the line drifts downward as heat carries energy off, and everything real slides down to settle in the nearest valley. It doesn't break the drawing, it just lets the line drop.
All right, I'll take the fine print, but step back a second, because this is a lot of faith you're asking of me. Why should there be a number that holds fixed at all? Kinetic, potential, heat, why do they always add up to the same total, come what may? Is that just a brute fact of the world, or is there a reason under it?
There's a reason under it, and it's one of the deepest things anyone has ever turned up. Energy is conserved because the laws of physics don't change from one moment to the next. The rules that governed the ball yesterday are the same rules today and tomorrow. Run the experiment now, or run it an hour from now, you get the same physics out. That sameness across time, that the laws don't care what moment it happens to be, is a symmetry. And every symmetry like that quietly stands guard over a conserved quantity. The one that time's sameness guards is energy.
Wait, energy is conserved because the laws don't change over time. Those sound like they're from two completely different departments. One's about a number staying fixed, the other's about the rules being the same on a Tuesday as on a Monday.
They sound unrelated, and underneath they're the same fact. There's a precise, provable bridge from the laws don't change over time to energy is conserved, and a later episode builds it plank by plank. For now, just carry the shape of it. The constancy of energy isn't a lucky accident. It's the shadow asymmetry of the world casts. When something in nature flatly refuses to change, it's usually because something else refuses to care about something. Here, the law's refusing to care which moment it is.
That's a genuinely strange and good thing to leave hanging over the rest of the series. A conserved number is the shadow of a symmetry. Filed.
Hold that shape. It's one of the through lines of everything still to come. Now let me gather the whole day back up in one piece, because we've covered a lot of ground, and it deserves to be said as a single thing.
Yes, do the gather. Wind it all back in for me.
Here's today in one breath. Energy is a bookkeeping number, and it comes in two pockets. Kinetic, the energy of motion, and potential, the energy of position. As a thing moves, the two trade back and forth, and their sum holds fixed. The tossed ball, all motion at the bottom, all height at the top, the same total carried the whole way. Work, a force acting through a distance, is how energy pours from one pocket into the other. And when the force depends only on where the thing is, you draw the potential as a landscape of hills and valleys, lay a flat energy line across it, and read the whole motion with your eyes. Fast in the valleys, slow on the hills, stopped and turning where the line meets the curve, trapped below the peaks and free above them, resting in the valley bottoms and never on the hilltops. Friction doesn't break any of that. It just scatters organized motion into heat you'd stopped counting.
And I never once solved anything. I looked at a curve and a straight line and read off where the thing races, where it stops, whether it's trapped or free. That still feels like getting away with something.
It isn't getting away with anything. It's what a conserved quantity is for. That's the shortcut I promised you at the very top, the one that saves you from grinding the crank. But now let me show you the edge of what energy can do, because that edge is the door to next time. Everything you just read off that landscape was about speed and about where the thing can and cannot go. Notice the one thing energy never once told you.
Let me think. It told me how fast, the gap gives me the speed. It told me where, turning points, trapped or free. What didn't it tell me? Direction. It never told me which way the thing is going.
Direction. Energy is blind to it. The kinetic energy of a thing moving left is identical to the kinetic energy of the same thing moving right at the same speed. Energy carries no which way inside it at all. You can even see it on the landscape. At any spot, the gap gives you the speed, but nothing in the picture says whether the thing is rolling left to right or right to left through that spot. Energy knows how fast. It never knows which way.
Which is fine for a ball in a valley where there's only forward and back. But the moment two things crash into each other or shove off each other, direction is the whole story.
And energy alone can't carry it. For collisions, for two things pushing off one another, for the strange, steady spin of a whirling, flying apart mess, you need a conserved quantity built around direction, one that carries which way inside it. And we've already brushed up against its shadow. Last episode, the third law, every push answered by an equal and opposite push, the handshake landing on two different bodies. Hiding inside that pairing was a quantity the pair never spends. That's the direction-aware one. Its name is momentum, and it gets next episode all to itself.
Momentum. Name only, no definition. I know the drill by now. Energy for how fast and how far. Momentum for which way. The two of them together.
The two of them, and between them they'll carry most of the mechanics you'll ever need. But that's next time.
One last worry before you send me off. This landscape trick, it only works when the force depends on where the thing is. How often is that, really? Or did we just build a lovely tool for one narrow little corner of cases?
Far from a corner, it's most of what you'll ever meet. Gravity, springs, the pull between charges, the forces that hold matter together. They all depend on where things are, and they all store and return. The landscape is the native picture for a huge slice of physics. Friction's the notable outsider, and we've already made our peace with it. So no, not a narrow corner, a main road. So leave with the picture, because it's the thing you'll reach for again and again. Whenever the force depends on where you are, you can draw the world as a landscape of hills and valleys, lay a level line across it for the total energy, and just look. The motion is in the shape.
The motion is in the shape. That's the one I'm keeping. That's the landscape of energy. And next time we go find out which way everything is headed. Thanks for climbing around the hills with us. Until then, when you want to know where a thing can go, don't reach for the crank, draw the landscape, and look.